my gosh. Okay, so I know that it's like the last talk of the day, and I was laughing because Paul earlier said, like, yeah, we're going to talk about the command line. I know it's 4 p.m., and I'm here like, it's 5 p.m., and we're about to talk about compilers. So I want to like give you a little bit of something that you can do to, apparently neuroscience says it helps you feel a little bit more awake. So I read it from I heard it from Andrew Huberman, and he said that if you are feeling a little tired, you can trick your brain into being more awake by looking upwards towards the ceiling for 20 seconds. So if you do that, sorry, this was all a ploy to get my friends to do that. Sorry, I had to. Now we're talking serious. Anyways, welcome to Build a Binary. I have to apologize because the title is a little misleading. We're not going to build a binary. We kind of did that earlier, which I was glad, so everyone got what they came here for. But yeah, let's actually start. My name is Anna Beltrami, and as you can tell from my accent and my name, I'm from Sheffield. No, you're laughing, but actually, one thing I used to do when I was a student at uni, I used to, after a couple beers, I used to tell everyone I was from Sheffield, like, yeah, I'm not actually Italian, I'm putting this on. And people believed it. They thought I was some anyways, I am a bit crazy, but not as far as to say that, I'm not. I'm Italian, I'm from Italy. I know there's a lot of Italians here, so put your hands up big. Yes, Italy! Amazing. Sorry, I had to do that. But yeah, so I am working at Spotify as a mobile infrastructure engineer in the area of developer experience and developer productivity. However, even though I don't really write that much Swift these days, I still consider myself an iOS developer. And what am I here to do today except annoy you a little bit? So my goal is to try and demystify and clear up how Xcode goes from your code into a hopefully functioning app. And that I hope through that I can help you feel a little bit more curious and empowered about the magic and underlying mystery of it all, which is really fun, I promise. I really enjoy all this stuff. And we're going to do this in like a very my way, which is unhinged. So by the way, I have a quick theory. My theory is that the more stickers you've got on your laptop, the more unhinged you are. So anyways, so we're going to follow a build failure that I encountered and kind of see where that takes us. And we're going to go through quite a few things. We're going to talk about compilers, the Xcode build system, what is an iOS binary, and then about some other possible alternatives. And yeah, I hope for many of you here it's going to be new information. For those that, you know everything, I give you a little challenge to pass the time. Try and count how many different rabbit holes you'd fall in and how many different things you'd have to research. And then you realize why it took me forever. There's a lot of things that we're going to talk about, but I hope everything can make sense at the end. And yes, I also have a QR code as customary. It's mandatory. You can't speak unless you've got a QR code. It's going to be there at the end for you to find it, or you can find it at bento.me/acbdev. And now let's get started for real. So last year, I spoke here and I gave a talk called Spark Your Creativity, the Power of Swift Playground. And it's a little bit of a different talk from this one. The talk was about how I use Swift Playgrounds and my experiences in it and how it really stimulated my motivation and my creativity and how I fell in love with Swift Playgrounds because of its limitations, not despite of them. And a quick clarification for those that don't know, Swift Playgrounds, I don't mean the Xcode playground files, I mean the standalone IDE that's available on Mac and iPad that lets you build, and I was about to say test, but not test. It lets you build and distribute your apps straight from there, which is really, really cool. And yeah, it can let you do that, of course, but there are a few caveats, as I said, some limitations. One of these caveats, sorry, I screamed. One of these caveats is that you can use, sorry, this is not my style to talk so poised and elegant. One of the caveats is that you can use Swift Package Manager. However, you can't use it for all types of Swift packages. And this is how my story began, because I wanted to import Firebase, okay? So I go in Swift Playgrounds, I add Firebase. You can add, it's very nice UI for adding your Swift packages. And then the package resolved And I was like, this is sorted. However, after I closed that little UI, then I saw this build failure, the bane of my life. The target type, Clang target, is not supported. So this was a failure that I'd never seen before in Xcode. So I did, I did some advanced so I did some advanced debugging. And the reason why I'm laughing is in my notes I wrote down Italian gesture of disbelief. So this is actually what it means. So my debugging meant, like, I Googled the error exactly as it was, and I clicked on the first result that I found. Yeah, this is as far as I went. But the first result I found was this that I found in the Firebase iOS SDK that said, thanks for the report. It turns out that Swift Playgrounds do not currently support Swift packages with Objective-C implementations. We are following up with Apple on this. Good, I thought. Of course, what can I do at that point? I'm like, oh, right, I can file a feedback of my own, but there's nothing much I can do. So I kind of left it. But this festered inside me. As time went on, it started to really bug me, the fact that I hadn't figured out what was happening. So I decided, okay, enough is enough. We need to try and figure out what is going on, because everything, it's not just magic and fairies and stuff. Everything happens for a reason in this world, right? So I was like, right, let's take the error message. Clang target is not supported. First part, Clang target, what on earth is it? Very simply, it's a class declared in Swift Package Manager. It's so straightforward, but I can't believe I didn't think about it. It's just a Swift Package Manager target that is based on the C family of programming languages. OK. So I looked for hints for the rest of it. Why is it not supported? Did they do it on purpose? Is there a reason for it? So I looked in the repo. I tried to find some hints and stuff, and I came up short. I'm 5'4", so it makes sense. But I decided to do a little bit more digging because I realized something, right? So Swift Playgrounds projects, all they are Swift packages with a special type of target, with a special type of executable target. So I was like, okay, so if I open this in Xcode, what happens? So I literally took the package, put it in Xcode, build, with the dependency. It built. So I was thinking, okay, it's built. It gave me a warning about it. It said, like, hey, you shouldn't do this. But besides for that, it built no problem. So I was thinking, okay, this is something strange. So something must be different behind the scene. So maybe Swift Playgrounds is lacking something compared to Xcode. And because I didn't really know much about how Xcode handles things, which is a very non-technical way to put this, I started to think about what's the first thing I know that Xcode does. Xcode compiles, I guess. So I decided to have a little look inside the compiler situation in Xcode, and together we're going to take a little peek into compiler land. At this point, if you're thinking of running because you heard the word compilers, you are out of luck because I bribed the Playhouse to seal the doors. So you're in here for a minute. I'm sorry, that was very threatening. So before we dive any deeper, I wanted to give you a general overview. This is very, it's very simplified and very general way of how compilers work. So first things first, we have our front end. Nothing to do with web development, but what happens, we start with our source code in a high-level programming language, such as Swift or Objective-C or other that I don't like, and we go through the parsing phase. So when we're parsing, we're taking our language, the code as we've written it, and then we chop it up into little bits called tokens. Tokens can be things like keywords, functions, and operators. And then we take these tokens and we construct something called the AST, which is the abstract syntax tree. And it is that. It's a data structure, a tree data structure. And the reason why it's that is not just because someone wanted to make sense of their $39 a month lead code premium. It's because it's actually very optimal, of course, if you have a tree to go through it. And we need to go through it because then we have the analysis time. We do two parts of analysis. The first one is called syntax analysis. And it says, it does what it says on the tin. So we go through the thing, and then basically we're checking for grammatical sense, like are our brackets matching, all these type of things. Then we go through semantic analysis, where it's a bit more of a logical check, like for example, is a variable declared before it's being used, and things like that. If everything passes and you're Gucci, then we have something called the IR, the intermediate representation. So then it comes a cool part, which depends from compiler to compiler. Some compilers don't have this, some have multiple type of this, spoiler alert. And it's the optimization phase. So we're taking the IR, we're doing some magic on it, and then we're left with the optimized IR. And then we get into the final part of the compiler situation, which is the backend. The optimization, sometimes it's part of the front end of the compiler. I forgot there's many of you up there. So the optimization is sometimes part of the front end of the compiler, sometimes part of the back end of the compiler. So I kind of put it in like a gray area at the middle. But now the code generation part is full-on backend. So you take your optimized IR and you pop out assembly code, which of course is designed for specific target architecture. So what's actually happening with Xcode? How does Xcode handle the compiler? I wrote that there was 2 compilers, but that is a lie, because there's 3 compilers that you get with Xcode. The third one is the docc compiler, which it doesn't compile your code into the final app. It compiles your comments into documentation. But it doesn't help you get to the final result in this case, so we're not going to cover it. But just so you know, that one's there too. So the first one, the first compiler is the Clang compiler. That for ages I thought it was the C-lang, and then someone corrected me. It's like, Anna, it's actually Clang, and I thought they were joking because it sounds a bit kind of weird, Clang, like a German swear word. But the Clang compiler is open source. And it's, as my slides say, used for C-based languages. And it's also based on LLVM. Now, LLVM, which is short for low-level virtual machine, do you think it's a virtual machine? It's not a virtual machine at all. It's a collection of compiler and toolchain technology, so just a bunch of bits and bobs, like I think about it. And Clang uses some of these bits and bobs, especially for the universal intermediate representation, so it's called LLVM IR, and also some parts of the code optimizations for it, and lastly, the code generation step. And this is possible because Clang is very modular, and it works great. And because it's so modular and versatile and uses these LLVM things, it makes it very extensible and usable beyond just iOS development. You can use it also for other things like academic research, not all, some type of Linux development, and also Android native development kit, which is Android in C. I said it all. And then we've got the Swift compiler, also open source, and as the name very kindly suggests us, it compiles Swift. And also, same as Clang, it uses LLVM for optimization and code generation, but I think it's kind of cool, the Swift compiler, because there's a few cool things about it. One of them is that the front end of the Swift compiler is responsible for a lot of features that I said we love, and it's more than love, because we couldn't live without them. For things like code completion and syntax highlighting. I don't know if you remember, a few years ago, there was an issue where in Xcode, sometimes the syntax highlighting wouldn't work, and I literally would get so mad. So now I know who's responsible for it. The Swift compiler has my heart. And other things are also very cool about it, not just this. Sorry for the digression. The other cool thing is that we have an extra step. So if you remember what was going on with the compiler, the simplified overview I gave you, in Swift we actually have something, before we get to the LLVM intermediate representation, we actually turn it into the SIL, Swift Intermediate Language. And then that gets optimized first, and then you've got the LLVM IR optimizations. The SIL optimizations are really important because that's where you get automatic reference counting optimization, generics things, lots of Swift-specific things. And then the LLVM IR, that's when you get more CPU and performance type optimizations that are similar to the Clang ones that you get. So, pretty cool. I mean, at least I think it's pretty cool. And, okay, so at this point, as I was researching, I spent a lot of hours, and I learned a lot about the compiler situation in Xcode. And then I was in the shower, and I had what I thought was a stroke of genius, which, you'll find out if it was a stroke of genius or not. I thought, okay, what if Clang target is not supported because Swift Playgrounds only has the Swift compiler, and it doesn't have the Clang compiler? And I needed to verify this because, I had this thought. It couldn't go away from my head. I had to figure out if it was true. And because I don't think I'm going to look that good in, a gray tracksuit, if you know what that means, and reverse engineering was out of the question, especially Apple software, I decided that I had to find another way to do it. And fortunately, I had discovered that, okay, so as I said, you can use Playgrounds both on Mac and on your iPad. If you use it on Mac, you can access all the build logs from Swift Playgrounds. Does anyone want to guess where these are? Except for the people that have seen this talk already, you don't get to play this game. Okay, no, if anyone, I don't know how to make the guessing work because I can't see you all very well. So I'll just tell you where it is. It's in the place that everyone loves to delete. Didn't I say? Oh, I did say that on there, so that's kind of, that was a horrible game. It's in derived data. And if you look in derived data, you can find all the build logs for all your builds, both in Xcode and in Swift Playgrounds. So when I saw that, I thought I struck gold, because I said, I'm going to figure out what was happening, right? Of course, Swift Playgrounds doesn't have the build report navigator, Xcode does, so I said, of course, everything that's happening will be shown here. So I found an XC activity log file format, and I tried to open it, and then I remembered, actually, you can't really read them. If you try and open an XC activity log format file, it's just a bunch of gibberish because it's a very compressed binary. Fortunately, there's a really cool tool called XClog parser that my team at Spotify developed a few years ago, and now it's maintained by the Mobile Native Foundation. And just brew install Xclog parser, and then what you can do, you can literally drop files there or access them with the path in some way, and you can parse them into lots of different formats, like JSON, or even nice HTML that shows you how long each phase takes, etc., etc. So it's really cool. So I tried to do that, and I didn't exactly find anything that was helping me. I found how much my builds were taking, which was very short because it's not that much code. But then I found more in the derived data. I found desk.xcbuild file, and it was also in a weird binary format. And I didn't know how to parse it, and I couldn't find how to parse it. So I literally made myself blind, scrolling through and trying to figure out the things that I wanted to find. And I found important things, though. First of all, as you can see from the top little picture thing, I found the exact version of the Swift compiler that Playgrounds was using. And I was like, OK, I'm getting closer. Then I found that it was using the exact same toolchain as Xcode. And then I also found this default compiler, blah, 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 LLVM, Clang. So I was like, OK, damn, my hypothesis is being disproven. But I was happy because it was still progress. So at this point, I was like, OK, Playgrounds build have and use, I guess, both Swift and Clang, and the same toolchain as Xcode. So at this point, I was thinking, maybe something else is going on, right? Maybe there's something else with Xcode. How does Xcode deal with the compiler? Maybe there's some stuff I missed. And this is where the good stuff starts. So I want to talk to you about the Xcode build system. I don't know why I did this. It sounds like I'm about to talk to you about a Hoover or something. But the Xcode build system is really cool. It's basically a set of tools that coordinates, manages, and orchestrates all the separate tasks and processes that are needed to get your code into an executable. What do I mean with task? A task is just a unit of work. For example, compiling is a task, linking is a task. But the build system is not in charge of compiling themselves. The build system is in charge of telling the compiler, telling the compiler what to do. And the Xcode build system is called XCbuild Not to be confused with Xcode build, even though if you try to Google anything about Xe build, all you're going to find is about Xcode build. Xcode build is a command line thing that basically allows you to perform a bunch of operations on your Xcode projects, like archive, build, distribute, etc., etc. You might be familiar with it if you use, like, I think Fastlane uses that, for example. But yeah, it's a different thing. And the new, not that new anymore, but kind of new version of the Xcode build system was released with Xcode 9 and Xcode 10. And, very cool, is written entirely in Swift. And that is what then paved the way for things like SPM, and it's built on top of open source project LL Build. Meet LL Build. LL Build is like a builder of builders, in a way, and it's like a low-level build system kind of thing. No, I said set of libraries, yes. Set of libraries and set of tools that then help you build systems. So it's the underlying thing for Xe build, for SPM, and also for the compiler driver. More on that later. And also, according to the Swift forums, it's used in Swift Playgrounds. So I was like, OK, so it's using the same thing that Xcode is using behind the scene. So yeah, I was pretty excited at this point. And I lost my train of thought because I improvised, and I shouldn't do that. Ah, yes, yes. So one really cool thing about LL Build is that it follows the LLVM principles of designing developer tools in a library format. So rather than just doing things that are very like, command, LL Build instead advocates to create your components for builds, like to interact with your components. No, LLVM suggests that you should interact with things in a library way, so like almost in an API, rather than CLI, which makes it, of course, like a lot more robust, a lot more, just cooler. And one thing that is maybe coming, that was suggested once again on the Swift forums, is LL Build 2, which is based on even more modern build systems, but we're gonna touch on that later. Sorry, water break. I've been screaming a lot. They should have a little music for this. Anyways, OK, now we know a little bit more about the Xcode build system. We know what's under the hood. We know about LL Build, which I mean, when I was starting to research this, I never even knew that existed. But what actually happens in practice? Like, what happens when you press the build button? So I wanted to give you another, like, kind of general, high-level overview of what is happening and what basically the Xcode build system is responsible for orchestrating. When you build a project in Xcode, this is kind of like what's happening at the high level. You've got your source code, which is written in, of course, like Swift. Like, it's supposed to be an Objective-C icon there as well, but I couldn't find one that was like high resolution enough. So that's the one you get. And that is, first of all, it's pre-processed by the compilers. And in pre-process stage, there's quite a few things that are happening. Basically, the code is streamlined for the rest of the compilation. Lots of things happen. For example, macros are expanded. For sure, Objective-C macros are expanded by the Clang. I'm not too sure if that's when the Swift macros are expanded, because I couldn't quite figure it out yet, but I will at some point. Comments are stripped out, etc., etc. So everything that's getting ready for then the compilation process, which we've covered already, blah, 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 everything that's happening. And then after the compilation, as I said, we end up with assembly code. The assembly code goes through the assembler, which is part of the compiler toolchain, so it's still kind of part of those. And it takes this assembly code, and it produces object files. Object files, object relocatable files, they're basically like things that the CPU can understand, but they're non-executable. Then these object files are banged in with a linker, and the linker, the linker is that girl, takes everything, adds a bunch of libraries, makes a nice little soup, and then you've got your executable, which the loader takes and loads into memory. But we're going to dive a little bit deeper into some of these components and explore. And we're coming back, first of all, into compiler land. So I wanted to show you here some of the things that I was wondering as I was researching, because I was like, okay, this is kind of like how compilation happens, but why is it that as I'm writing code, I'm getting syntax errors? And that is because when you're writing code, like as you're writing, the front end of the Swift compiler is active. She's ready to go. And as you're writing, it's parsing everything into the AST, which is then, I didn't put a label on there, but that's like a cache. So it's parsing, it's caching, and then if you make any mistakes, it feeds it back to you as errors. And that's when you start crying and then it was something very easy. And that's one scenario. So as you're writing code, this is kind of what's happening. The other scenario is you've got a clean build. When you've got a clean build, the first thing that happens at a high level, once again, is the cache that you've just worked so hard to populate is cleared. Of course, that's why it's called a clean build. And you go through the full compilation once again. As things are made, they're put back into the cache. And then you carry on building as normal. But then, in an incremental build instead, you're taking the things that are cached and you're continuing that way. That's why an incremental build is, well, not why, but part of why incremental builds are a lot faster than clean builds. So who's in charge of this situation? Is the build system telling like what to cache, what not to cache, what to clear, et cetera, et cetera? No, because we've got the compiler driver. So the compiler driver is very simply a program that is coordinating the compilation of Swift code into all these various results that we need. And I have not put my timer on. Okay, I might have to go through this a little bit quick because I have made a crucial mistake. You know Job in like Arrested Development? I've made a huge mistake. That's me now. Anyways, so the compiler driver is like basically a mini build system for the compiler. And it's what orchestrates like kind of, as I said, what to compile, like the order, et cetera, et cetera. And this is like a very high level overview of how it's working. But because I don't want to risk it, I'm not going to go too deep into it. But then I will, if you find me later with a beer, I'm going to explain to you how the compiler driver works. Fantastic. I'm great conversation. Anyways, after this important part of the compilation process, what we need to remember is that we're left with assembly code. And what happens? We get the assembler. And as I said, the assembler very briefly 10 minutes. Okay, very briefly put, takes the assembly code and it turns it into machine-level instructions and something that the CPU can execute at some point. And the output is a bunch of relocatable object files, which are noted as .o files. And then you're left with something else, but hold your horses. So after the assembler has done its job, here's where like my favorite part, right? My favorite part happens. We have the linker that steps in, takes all the loose ends that we've got, ties them together, and we produce a final Mac-O executable. So we know how this, like, we know basically this is what happens, but how, as I said, like it takes also the library, so not only the .o files that we have produced through the compilation process, the assembler, it takes also these libraries. So there's a few, like, I wanted to show you with an example that I've thought up, and this is like basically a summary of these two WWDC videos that I watched from last year, which are really, really good. So I recommend you watch them for more precise and like, you know, more Apple level of explanations. So for the first example, we've got a static library. Static library, which is just a bunch of .o files. What happens is the linker goes through these files in a procedural serial order, so one after another, and they're checked against the symbols table. Symbols table is basically like the VIP list of a club, okay? Stay with me, the metaphor will make sense. As we're checking these files, we're checking for two things. One thing is a use of a symbol which is like, for example, a method. So we're checking for uses, and we're checking for definitions. If the linker goes through and it finds, as I said, in procedural order, file by file, it finds a use, it pencils you in to the VIP list. Nice. And then if it finds a definition, then you're in the club. If it doesn't find a definition, that is when you get undefined symbols error, which I think some of you probably have encountered. So that's all good. If you find if it finds a definition but it doesn't find a use, there's no point having you in the club, so you're not in. And that's fine, because that means that we only have what we need. And when I say you're invited to the club, it means that the code from the static libraries is then copied into our final executable. However, something happens a little bit differently with dynamic libraries. Now, with dynamic library, rather than having a bunch of .o files, we have a single executable mac.o file. And we're still able to check through the symbols table the same way. But if you're in the club, instead of getting code copied in, because of course this is all, like you can't really do that, we're getting a promise that at runtime, the DYLD, dynamic linker, is going to execute the code that we will need to execute using the path of the library that we pass in. So this is something really cool that you can explore on your own if you're interested in like reverse engineering, because that's a lot of shenanigans can happen here and often happen here. So yeah, it's really, really cool. And I hope that made sense with my strange metaphor. But one cool thing that I wanted to also say is that in Xcode 15, we've got a new linker, the LD prime, which sounds a bit like a bad transformer, but it's really cool because a bunch of people have benchmarked like how much faster their build times are thanks to the LD prime. And it showed like really, really big improvements. And if you can't use, for some reason, if you can't use Xcode 15 yet, the good news is you can backport it to Xcode 14. So cool. OK, so what is the end product of all this kerfuffle? What are we left with? And I guess now we're at the binary part of build a binary. So first, where is the app binary? I used to confuse myself with this a lot, because at one point I thought the IPA was the final executable, and it's not at all. So if you take the IPA or the XC archive, and you basically like unzip and you manage to look inside, way easier with the XC archive, but it's done trivially with an IPA as well, you're going to find like a bunch of things. You're going to find the dynamic symbols, which are needed for debugging your crashes. You're going to find info plist with a bunch of team and signing info, and then you're going to find products. In products, you have your app bundle. Once again, that's not the executable yet. If you look inside the app bundle, you find like a bunch of things, but what we want to look for is the universal fat binary. And I am not being rude in calling it fat, because that's the actual name. And there's a reason for it. It's called the fat binary because inside it embeds multiple formats for different architectures and CPU types. As you can imagine, the latest type of fat binary from Apple is one that allows you to both basically, it has support for both 64-bit Intel and Apple processors. And yeah, that's pretty much how it works. The fat binary uses these fat headers to like embed the two different macro files. And yeah, the macro file being the final like executable bits. And what are they like inside? This macro file, basically a Mac object, it's a file format for native macOS and iOS executables, and it has three major regions inside. You've got a header, you've got load commands, which basically tell you like a bunch of linkage information that, as you said, that we need earlier. And then you have segments like this. I wish I had more time to look into this and to explain it because it's really cool. But maybe now you will understand my favorite joke I've ever made in my life. I mean, I liked it. It's layered. Afterwards, with a beer, I explain. So, OK, at this point, you're probably wondering, all right, now I understand a little bit about what's going on, but is the Xcode build system the only way to go? Is there any other alternatives? And the answer is there's plenty of alternatives. And there's plenty of other build systems. For example, CMake, GNU. Like, for example, before Xcode 3, Apple used another one that I do not remember, and I'm going to kick myself in the back for this. But the one that I feel like I can talk about a little bit is Bazel, because I have some personal experience with at Spotify. So Bazel has a tagline that says, fast, correct, choose two, which I think is pretty snazzy. And it's an open source build system, open source by Google, based on their very powerful internal build system called Blaze. You might have heard, like, some people confuse it with Bach, and it's kind of funny because according to a podcast I was listening, the reason why Bazel was open sourced, well, Blaze was open sourced into Bazel, is because, like, as time went on, Googlers were leaving Google and going to, Facebook, Meta, etc. And when they were there, they decided to basically implement Blaze. So that's why at one point Google is like, OK, fine, open source a thing. That's what I heard, though. That's the gossip in the podcast that I heard. So one important thing to note about Bazel is that it's artifact-based build system, while Xcode is a task-based build system. And Bazel is cool because if you have an absolutely behemoth, massive type of code base, like a monorepo with a bunch of different languages and really weird architecture and tooling, you have insanely big reductions in build times. And even though it's something like really cool, and I do enjoy working with it, I will be honest with you, the learning curve is kind of like a bouldering wall. So be careful. Like, I think every time I give this talk, people ask, like, should I use Bazel? And I'm like, I don't know, but be prepared because there is a learning curve. It's not impossible, though. It's fun once you get used to it. But the best benefit that you will get from it is if you have, like, as I said, a massive code base. Like, for example, at Spotify, we use Bazel for many things in the iOS world. You can use it for more things, like, outside of iOS. But for iOS, we use it for generating our iOS project, because we don't commit our XC project files. We use it to build locally and to build on CI as well. And, for example, for us, like, we have, like, millions of lines of code, and lots of complicated architecture, and like over 200 iOS developers. If we were just using like XCbuild and vanilla Xcode as its package, we wouldn't even be able to open the IDE. So we've had to find ways of making this work. So I would like to explain to you how Bazel works, but I see a very scary number at the top, so I need to go. But once again, I can explain it to you. But one of the main, like the important part is like lots of things are happening here to build that are a little bit different to the way that Xcbuild works. However, you're going to be left with a bunch of artifacts from the build process. And these are something that you can cache, that you can reuse, that you can execute remotely, which is part of why Bazel is so much faster for some people. And that also ties back on the concept that we have task-based versus artifact-based build system. In a task-based build system, like Xcbuild, it's very powerful because you're focusing on how to build something. So you can define like whatever you want, but of course with great power comes great responsibility. And instead with an artifact-based build system, we're focusing on what to build, and that makes it that our builds are a lot more consistent. And something really, really cool, sorry if I'm rushing, is that Apple, as I said, is maybe coming out with LLbuild 2. It's in the works, but LLbuild 2 actually uses the Bazel remote execution API, and it tries to be a bit more artifact-based rather than task-based. So if that happens, I guess we won't be able to do this anymore. Okay, so don't worry, like I'm concluding. At this point, you might be thinking, wow, like we've gone through absolutely everything, but Anna, what about the playground failure? At this point, did you figure it out? What do you think, Enrico? Do you think I figured it out? No, exactly. I was hoping that you'd say yes and show some faith in me, but no, I haven't figured it out yet. However, I feel like, yes. It's going to stay for now like top 10 iOS unsolved mystery. I don't quite know what's happening, but trust me, I haven't given up. I'm doing everything I can to figure out what's happening. Come next year, because maybe I'll have a solution. But you might be thinking, okay, you haven't fixed it. Is this all a waste of time? I feel like it wasn't, because for me, as I went through this, I've discovered so much about Xcode, how it works, and compilers, and I've gained so much foundational knowledge. And one of the most positive benefits is I got myself into the habit of always asking how and why, instead of just shrugging it off and saying, like, I guess it is the way it is. And as I did that, I discovered so much about the joy and the fun of exploring things in a kind of an unhinged and chaotic way. And as I fell into another rabbit hole, I discovered that there's two different types of curiosity. When you have a deprivation-based curiosity, basically you're driven by FOMO, by negative emotion, then you need to figure out things because you have to, because your mate knows and you don't know, and you're not driven by the pure passion of learning random stuff all the time. While interest-based curiosity instead is much more joyful and positive kind of curiosity that psychology actually recommends that we put a lot of effort in to nurture our own and to have it grow. And someone who agrees, I guess, with this sentiment is none other than Albert Einstein, that says, this is probably my favorite quote ever. He said, "I have no special talent. I am only passionately curious." which I think is amazing, because if Albert Einstein is saying that he has no special talent besides his curiosity, maybe that can tell us, and it definitely told me, that we can nurture it, we can let it run free from time to time, because that's how we're going to get a lot of benefit, I guess. And it's also very fun. And believe it or not, this is an actual authentic quote by him from a letter to Carl Selig. I know they get him to say all sorts of things, but you can verify this. He said this. And I wanted to leave you, I promise, sorry, James, with a final quote, very profound, that he said. And couldn't have said it better myself. And now I'm finished. Thanks to everyone who helped me prepare this talk, and to SwiftLeeds for organizing this amazing conference and for selecting this talk. And most of all, thank you for listening. And sorry if I took a little bit longer than I should have. Thanks.